There are two new ideas in this lab activity. The first one is has to do with a new way of showing whether an object is speeding up or slowing down. And I'll talk about that first. The second one is Newton's first law. That isn't something that's been useful to us for calculations, but we'll see that intuitively it is sort of a useful idea, and I'm going to talk about that. And then I'll give a little problem-by-problem description of what to look out for on these problems. Okay, so the first idea is this new way, a new way to show whether an object is speeding up or slowing down. So far, what I've done when in these problems where I ask you to show the direction of the velocity vector and the direction of the parallel part of the acceleration, perpendicular part, figure out what you know about the total acceleration and net force. I've done it something like this. I've said like, okay, this is the path the object is traveling along, and it's going this way. And, you know, I might say like, okay, up until here, it's speeding up. And then after that point, it's slowing down. Well, this could also be shown, and this is a very natural way to show it if you're figuring this stuff out from an experiment. You could take think of it as a photo, a snapshot of the location of this object every 10th of a second or every 50th of a second, as long as you have regular intervals that you're taking these snapshots. How far apart the object is in those snapshots tells you whether it's speeding up or slowing down. So for example, let's say that this object, you take a picture, a first picture here, a 10th of a second later, you take a picture, and the object is here, and then here, and then here, 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 here. Well, what you see in these pictures is the distance between every pair of positions. The distance between them is getting bigger. And if the distance now we're talking about every time we take a snapshot, it's the same amount of time that's elapsed. And so if this object starts out going a small distance and is going farther and farther and farther in that amount of time, that means the object is speeding up. So instead of me telling you that the object is speeding up over the interval, I can say that if we're looking at every 10th of a second or whatever, these are the locations of the object. You can visually see that the object is speeding up. And then on the other hand, if it now, after it gets to this cutoff point here, now it starts out far apart, and each time you take the new picture, they're closer together. Then if every one of these time intervals, the object gets closer together, now it's slowing down. And so without telling you it's speeding up or slowing down, you get the same information by seeing the snapshots of the object over those regular intervals. Okay, so let me show you how you could use this for like a lab question. And there are a couple of questions like this that you'll have to do. So let's say that the object, well, I'm going to do it. I'm going to basically recreate this same thing that I just did. Okay, so let's say that the object is going this way along the path. And let's say that we have 2 points that we care about. I'm going to call this the point A and the point B. Okay? Sketch what you know about the velocity vector direction, the part of the acceleration parallel to the velocity, the part of the acceleration perpendicular to the velocity, and the direction of the net force at each of those 2 points. Okay, well, just to make it a little easier to follow, I'm going to sketch the path of this object. Okay. And we know which way it's going, so I know at the point A, the velocity is tangent to the path. This is all stuff you've done before. But now we have to think, okay, if the snapshots are getting farther apart when we're at the point A, which way is the parallel part of the acceleration going? If they're getting farther apart, it's speeding up. So we know that the parallel part of the acceleration is the same direction as the velocity. And then which way is it turning? You can see that from this point A, the path is going to the, in this direction, if you can see my cursor, from the velocity vector. So we know that the perpendicular part of the acceleration, is this way. And so the total acceleration has to fall somewhere between these 2 parts of the acceleration. And if the acceleration is somewhere in that direction, then the net force has to be whatever direction the acceleration is. And so without saying in words whether this object is speeding up or slowing down at A, we can tell from these snapshots that it's speeding up at A. And at B, what can we tell? Well, the velocity is this way. When you're at B, you can see that these snapshots are getting closer together. The locations are closer together every one of these intervals. That means it's slowing down. So the parallel part of the acceleration is this way. It's turning this way. So that's the perpendicular part of the acceleration. And since the total acceleration is the sum of the parallel and perpendicular parts, it has to be somewhere in this range of directions. So this is the direction of the total acceleration, somewhere in there, and the net force is also somewhere in that range of directions. So you have a couple of problems like that. One where it's moving in a straight line. And remember, if something's moving in a straight line, it's not turning. That means there's no perpendicular part of the acceleration. And then another one where it is turning and changing speed, and you have to do basically what I've done here. Okay, so that was the first thing that's new in this lab activity. And then the second one is Newton's first law. And Newton's first law says if no net force is acting on a body, then the body moves with a constant velocity. And moving with a constant velocity means that it doesn't turn and it doesn't change speed. So it moves in a straight line. With a constant speed. The reason that we haven't talked about Newton's first law is that for calculations, it's not very useful because it's contained in Newton's second law. Notice that Newton's second law tells us that if there's no net force on an object, Newton's second law, let me write that first. So if you add up all the forces on a body, it's equal to the body's mass times its acceleration. So what happens if there's no net force acting on the body? If all the forces add up to 0, then F net is equal to 0, and that means acceleration has to be 0. And 0 acceleration means constant velocity. So Newton's second law doesn't add anything to our ability to calculate that wasn't already in Newton's second law. But it is a nice intuitive thing. It's a useful thing to think about. And so you'll have to do a few problems where a body goes from having a net force on it to having no net force acting on it. And you'll have to recognize that once the net force becomes 0 on that object, the acceleration also becomes 0, and therefore the body starts to move in a straight line with a constant speed. Okay, so let's talk about some of these problems that you're going to have to do. The first one, number 4 in this lab activity, is one where a body is moving around a circular path connected to a string. And so let's say it's moving around this way. Okay. Well, while the string is attached, this body is turning. And so it has an acceleration that's toward the center of the circle. But then at some point it says, now imagine that the string breaks. What happens to this body? Well, notice that if you're taking the view of this ball that's traveling around this circle from above, that once the string breaks, there's no force acting on this. A free body diagram would show no forces on it. There would still be gravity going into the page and a normal force coming out towards you out of the page. But you wouldn't see those in a two-dimensional free body diagram if your view is from above. And what that means is that once there are no forces acting on this ball, that ball is going to stop having any circular part of its motion. Its acceleration is going to go away, and from that point on, the ball is going to continue in whatever velocity it had at the instant that that string breaks. And so that's the first thing that you have to recognize for number 4. Number 5 is sort of a similar idea. You have an object, it says it's in space, so you don't have to consider gravity at all. And you have a ball that's moving along a wire. I guess you could think of it as like a bead. It has a hole in it, and it's sliding along this wire this way. Okay. As long as the ball is sliding along the wire, that wire is making it turn. And so it has accelerations, net forces, things like that. Although the speed is not changing, and it says that in the problem. But once it gets to the end of the wire and leaves that wire, now if you draw a free body diagram of that bead, there are no forces on it anymore. And so again, once it leaves that bead and there are no forces on it, you know that that bead is just going to continue in a straight line with a constant speed in the direction it was going at the last instant it was in contact with the wire. So that's sort of similar thought process to number 4. Number 6 is basically the same. It's a tether ball setup. And so this ball is moving in a circular path if you think of it from above. And again, the string is going to break. And once that string breaks, the forces that are making it move in a circular path disappear. And that ball starts to move with a constant velocity. The one thing that's different about number 6 is after number 6 asks you to analyze what's happening from above, it asks you to analyze what happens from the side when that string breaks. So let me draw a picture from the side. Okay, so let's say this is the string, and now this is right at the instant that that string or that tether breaks. Okay, and there's the ball, and here's the post that it's swinging around. Okay. At that instant, from this view, notice that the ball is moving in this direction. Okay. So its velocity is that way. But notice in this view, if you draw a free body diagram, and it does ask you to do that, draw a free body diagram of the ball at the instant that this breaks. Well, from the top view, there are no forces that you can see. But from the side view, the weight is acting straight down toward the bottom of the page. And so now there is a net force acting on the ball. And so from this side view, you will not see this ball have zero acceleration or a constant velocity. From the side view, it'll look like projectile motion. And so it asks you to think about, so now this ball is moving with a velocity that I've shown here, and the only force acting on it is the weight. It asks you to, think about the motion in terms of what you know about projectile motion. Then in number 7, this is pretty similar to ones you've done before. You have a ball that's rolling down and then up a ramp, and then it's in projectile motion. You just have to think about the way that we have for a long time now. What's the direction of the velocity at each instant? Is it speeding up or slowing down? Based on that, what's the parallel part of the acceleration? Is it turning? Which way? Based on that, what's the direction of the perpendicular part of the acceleration? And then figure out what you know about the total direction of the acceleration at those points. The one thing you have to remember about number 7 is that the object is going to be speeding up when it's on its way down, and it's going to be slowing down when it's on the way up. And we know that from conservation of mechanical energy. And then numbers 8 and 9. These are problems where you're given photos in sort of funny views, and you have to choose a new view of the problem that sort of makes this problem make sense. For the motorcycle, you're going to want to choose a view from above. So the motorcycle's moving around a path this way. There's the motorcycle. So even though you don't see this view in the photograph, this is the view you want to choose to analyze it. One thing that's worth noticing is, so I don't know, I'm not a real expert in drawing motorcycles, but okay, so here's the motorcycle guy from a front view, okay? A free body diagram would look like this. The weight is acting, let me draw it a little straighter. The weight is acting straight down. There's a pushing force from the ground that's keeping the wheel from sinking into the ground. But there's one more force acting. There has to be a horizontal force because otherwise there's no way that this motorcycle could continue in a circular path. There has to be a horizontal force that's causing a horizontal acceleration. And it asks you what that force is. Notice that what that force is a friction force, and it's acting like in this direction. And the way you can make sense out of that in your mind is notice that like visualize a motorcycle going around a turn and imagine it hitting a slick of oil or a patch of ice or something. What would happen? The turn would immediately stop, and the motorcycle would immediately, at that point, continue in a straight line in the direction it was going. That is because the only thing that's providing the force necessary to turn is that friction. And then the last thing I want to say is for number 9, it's these two cars crashing into each other. It looks like maybe they're turning or doing some funny kind of thing. But what I want you to think about with that is that these two cars are going straight towards each other. And once they make contact with each other, all they're doing is slowing down. They're not changing direction. Okay. And that means that the only part of the acceleration that's happening once they collide is a part that's parallel to their velocity vector. Okay, so that's all I have to say about this lab activity. Please get in touch with me if you'd like to talk about it over Zoom or if you have any questions over email. And good luck.